Yes, Assalamu alaikum students. Good afternoon, everybody. We are at this time trying to deliver the lecture number 11. It is on vector calculus. Then we have before this discussed this lecture number 9 and lecture number 10. There we have introduced the line integral, and we are doing at present the applications of line integral. The first application we did, that it was that the line integral, with the help of line integral we can find out the work done by a force in moving a particle from along a curve in the space from one end to another end. That was the work done by the force. Now this time we are touching second application of line integrals. It is a circulation. Circulation is actually fluid dynamics. I will introduce this, what we mean by this circulation. In circulation we write, in fluid dynamics if V represents the velocity, V represents velocity of a fluid particle along a curve C, then the line integral, in fact along, we must mention here, along a closed curve C, along a closed curve C, then the line integral given by this line integral along the closed curve C, V dr, you know what does dr represent for? B dot dr gives the circulation. It gives what? The circulation of V around, gives circulation of V around closed curve C. So this is the second application of this line integral. With the help of line integral we can find out the circulation of the vector function. It may be a velocity, it may be some force. This gives the circulation. Now I will write one more thing here. Some authors in different books give you also the third this representation of this line integral, that I will discuss here. It is further if the circulation of V along every closed curve you can use the word here, V around every closed curve in a region D vanishes. If the circulation of V around every closed curve in a region D vanishes, then V is called irrotational. we will be called now irrotational in domain D. Actually, you have one more test for testing the irrotationality of any vector point function. If you remember, in our previous lectures we have mentioned there, if the divergence of any vector vanishes, what is that vector called? It is a solenoidal. If the curl of any vector vanishes, what will be the vector called? It will be a rotational vector. So you have one more test for irrotationality of a vector. It is this: if the circulation of any vector in a along a curve vanishes, then we say the vector will be irrotational. Thus we say, if line integral over the closed curve C f dot dr is 0, if it is 0, then f is irrotational vector. It is a irrotational vector. So this is also the another test for irrotationality. We have one more test for irrotationality. So in this way, in this application, first application, we did how to find out the work done by a force with the help of this line integral. Now in this lecture we will see how to find out the circulations of a vector, of a function, vector point function, by the line integral. Now I will touch some examples of this application. Actually we are doing at this time application part. I will touch some applications how to find out the circulations along a closed curve. I will write some. So I have written here some applications. Let us deal these with applications on the how to find out the circulation. First one I wrote, find the circulation of f around the curve C. Curve C is given by this, where f is this, f is the vector point function this, and C is the circle, closed curve is this, x square plus y square is equal to 1, z is equal to 0. And second application we will do next. Let me have the solution of this application number 1. Solution of first I will write here. You are given a circle. You are given. Take this theta here. This is your origin, which is 0.11 here. Circle is x square plus y square is equal to 1. Its equation is z0. This is the equation of the circle. We have to find out the circulation of this force f, vector point function f, along this. Now given equation of circle is x square plus y square equal to 1, z is equal to 0. Okay, we have parametric equations. Parametric equations of circle are, as you know, when we have the equation of the circle x square plus y square is equal to r square, then we take the parametric equation as x is equal to r cos theta, y is equal to r sin theta. Here r is your radius of this circle is 1. So we take the parametric equations are x is equal to cos theta, y is equal to sin theta. Theta is the angle that it makes somewhere here. X cos theta, y sin theta are the parametric equations of this circle. So that you will write now vector r is it is xi plus yj. Z is here 0. You can write even here zk. Your z is 0. This is not the circle in this plane. It is a circle in space because it is in the xy plane. Z is 0. Well, this gives you r is equal to your axis parametric equation cos theta I plus sin theta j. When you write here dr, because we need dr, what is this? This is minus sin theta I plus cos theta j. Also you have the vector function. Function is, it is given by y I plus zj plus xk. It is the vector point function. We have to find out the circulation of this f along the given circle, which is given by this curve. Is our curve is here this c, the full circle around the circle. This is f is equal to, you give y. What is your y? It is sin theta I, because by taking the parametric equations it becomes very simple, plus z is 0 plus cos theta k. Therefore, what is the circulation? The circulation around the circle, thus circulation of f around the circle C is given by line integral C f dot dr. What is this now? It is your curve is the full circle round the circle, so your theta goes from 0 to 2 pi. Let us first write it. What is this? F is your sin theta I 0j. I will write here C plus cos theta k dot, it is sin theta I plus cos theta j. It is d theta here. I'm sorry, d theta is here. Into d theta you can write. Well, it is along the curve C. When you compute this, it is minus sin square theta plus 0 d theta. This will be your integral. Now along the curve our theta is 0 to 2 pi, because this circumference of the circuit is it is from 0 to 2 pi. It is around the circle. It moves from 0 to 2 pi, full circle. This is minus sin square theta d theta. It is minus integral of 0 to 2 pi. How you integrate sin square theta? You will write it 1 minus cos 2 theta by 2 d theta. I am using the formula for sin square theta, which is 1 minus cos 2 theta by 2. Well, integrate this. This gives you circulation of f around the circle is it is minus 1 by 2 integral 0 to 2 pi 1 d theta, then plus 1 by 2 integral 0 to 2 pi cos 2 theta d theta. This is minus 1 by 2, this is theta from 0 to 2 pi plus 1 by 2 integral of cos is sine 2 theta by 2 from 0 to 2 pi. Okay, so it is a very simple problem. This was simple one. This is your minus 1 by 2, it is 2 pi minus 0, this is plus 1 by 4 sine of 4 pi minus sine 0. This is your minus pi, this is 1 by 4. What is sine 4 pi? Sine n pi is in fact 0 for all values of n, integral values of this n, this is 0. So you get circulation of f along the circle is given by minus pi. This is the circulation of f given by this. This is in fluid dynamics, and what it means there, you will apply the in physics. It is application there. What does it represent? Let us have second problem. You see, in second problem is interesting one. It is find the circulation of f. Find the circulation of f around the circle C. Given force is given vector function is f is equal to it is 2x plus y square I plus 3y minus 4xj. This is the given force, and circulation is to be found along C, which is given by, our C is given by y is equal to x square. It is a parabola from 0 0 to 1 1, and y square is equal to x from 1 1 to I am writing this question again. Maybe this may be not visible to you, so I wrote this question. The problem is to find out the circulation of f, where f is given by this, and curve along the curve around the curve C. The curve C is given by two parabolas. Y is equal to x square from 0 0 to 1 1. Another parabola is y square is equal to x from 1 1 to 0 0. I will just explain this concept to you. What this problem, very important. Such problems are usually asked in the examination. You see what is the representation of this. This is your one parabola goes this way. This is your parabola. This parabola will be y square is equal to, this is y square is equal to x. This is y square equal to x. And second is, I will rub it here, second is x square. Second is this parabola. This is your x square is equal to y. Okay, this is our curve C. This is the point 0 0. We will find out this point how it is. This will be the point P 1 1. Now we have the two parts of this curve. One part goes this way, anti-clockwise. This is C1. Then from this to this, it is C2. Means our given curve C, this round the which we have to find out circulation, is divided into two parts. One is curve C1 of x square is equal to y, and second is of this C2, which is along the parabola y square is equal to x. We have to find out the circulation now. Now solution part we will write, given equations of parabolas are, one is y square equal to x, then x square is equal to y. Okay, solving these 4 points of intersection, if we solve, we will of course get this point and this point. Let us see, solve first and second for what? Point of intersections where they meet. Actually it is obvious the two parabolas meet in the first quadrant, so there is no possibility of the negative this intersection. The intersection will be positive. Solve this and this. If I using this value of x, y, use y in, use second in first, that is value of y. It is x4 is equal to x. This is x4 minus x is 0, implies x times x cube minus 1 is 0. This gives me x 0 and x cube minus 1 0. When you write x cube minus 1 0, what is this? X minus 1 into x square plus x plus 1 is equal to 0. This gives x minus 1 is 0, gives x is equal to 1, and this gives x square plus x plus 1 equal to 0. If I solve this for x, what does this give you? X minus 1 plus minus under root of 1 minus 4. It is rejected because it gives me imaginary value of x, so I reject this. Therefore only possible values which also lie in the first quadrant. So we take x is equal to 0, that we have got here, and x is equal to 1. Using in first or second, when x is 0 in first, you get y 0. So point is here, origin 0 0. When you use x is equal to 1, using x is equal to 1, okay, you use x is equal to 1. In y square is equal to x, use x is equal to 1. What is y square? It is 1. Y is plus minus 1. So in this case I get the points 1 1 and 1 minus 1. This is also not used because the intersection, our curve lies in the first quadrant that we have seen. We also reject point 1 minus 1 as the curve lies in first quadrant. So only points are points of intersection that gives us curve 0 0 and 1 1. 0 0 1 1. Now you see, when I find out the circulation, in circulation I have now two parts. I have to find out the circulation along this curve C1. It is x square is equal to 1. Here we have x0 to x1. Then from this, if I write that in terms of y, we can write in terms of x also. If you go from this, then you have y1 to y0. So this gives the complete closed part of this curve C, which is bounded by the one part of the parabola and second part of the parabola. We have to find out the circulation, a line integral along this curve along this part, then plus this part gives us the whole curve C. Okay, let me see now. So I write here, thus the circulation of F around the curve C. Curve C is what? Given by y square equal to x and x square equal to y is, it is line integral over C. Now this C will have two parts, C1 and C2. It is what? F dot dr. It is your C. What is your F? You write your F is given. Your F I have rubbed it there. Your F was, what was your F? I will write it from the problem. It is 2x plus y square I plus 3y minus 4xj. This is your F. 2x plus y square I plus 3y minus 4xj, then it is dot, it is I dx as usual. This will be I dx plus j dy. This is your our C. This will be I dot I is 1, 2x plus y square dx, then plus 3y minus 4x. This is 3y minus 4x dy. This is the circulation of F along C. We name this alpha. Now we find out the first two parts separately. We have now along, or we can say in this way, the given curve C is closed by C1. It is closed by C1 given by what? This C1 is given by y is equal to x square from what? From, if you use x here, from x0 to x is equal to 1, and it is closed by C2 also. C2 is given by what? You just look there, C2 given by, C2 is this, given by x is equal to y square. If you use y in terms of, you can write this in terms of x or in terms of y, it is up to you, but in the problem it is mentioned, I am going accordingly. X is equal to y square from y is equal to 1 to y is equal to 0. I am just coming this way, anti-clockwise direction. I am going this way. I am finding out the line integral along this. It is the one part of the curve C1. Then line integral along this. It is the second part of the curve C, that is C2. The sum of these two line integrals, this one plus line integral along this plus line integral along this, gives the line integral of the given vector function along this curve C, which is bounded by two parabolas. This is the question. Now let us find out C1 separate. I need this alpha. I will not rub alpha. Let me write alpha there. Let us go this way. Now along C1, what is along C1? I have y is equal to x square, implies dy is 2x dx. I will use dy 2x dx and use y is equal to x square. I will use there y equal to x square, so that the whole curve gets in terms of x, and I have to use naturally the limit for x. I have to use the limit x running from 0 to x is equal to 1. What does this give me? This gives me along C1 line integral. I will write here along C1, it is f dot dr is integral, line integral along C1. Well, look from alpha, you go to this alpha. I have this x as it is 2x. I have to replace y by x square, so this is your x4. Okay, this is dx as it is, then plus 3y, I have to use x square, it is 3x square minus 4x, but here it is dy, I have to use this dy by 2x dx. Okay, I have to simplify this now. I need this integral. Why not to write this integral here so that I can rub it? I will write it here. Integral this circulation of f is it is 2x plus y square dx plus 3y minus 4x dy. This is my alpha. Circulation of f along C, it is circulation of the f along C, it is 2x plus y square dx 3y minus 4x dy. It is alpha. I wrote it there, so I don't need this now. Let me evaluate this now. What is this? This will be now, it is dx here, it is from 0 to 1. This is now 0 to 1. Take it here. This will be, this is 2x plus x4, 2x plus x4. This is 3 to the 6 x cube minus 8 x square dx. Let me simplify this. 0 to 1 it is 6 x cube dx plus 0 to 1 x4 dx, then minus 8 0 to 1 x square dx plus 2 integral 0 to 1 x dx. Yes, it is 0 to 1, 2 times x dx, it is there, x4 0 to 1, it is there here, then 6x cube, it is here, minus 8, it is integrate this. This is your 6 by 4 x4 from 0 to 1. This is plus 1 by 5 from x5 0 to 1. It is minus 8 by 3, it is x cube 0 to 1, it is plus 2 by 2 x square 0 to 1. I am just integrating this. By integral, what you get? Well, this is your only 6 by 4, it is 1 minus 0, it is plus 1 by 5, it is minus 8 by 3, this is plus 1 minus 0, it is 1. So you can take here LCM, here, or it is 2 3s are 2 2s are. Let us take 30 here LCM. I can take 30 here. It is 45. It is plus 6. It is minus, what is this now? Minus 80. This is your 51 minus 80 by 30. This is equal to, just see, have I done here, is it, I'm doing correct? 6 by 4 1 by 5 x 5 8 by 3. 1 by 5 minus 8 by 30 LCM. Yes, it is plus 30 here. Plus 30. This is 81 minus 80. It is 1 by 30. This comes out to be 1 by 30. This is your 1 by 30. Well, along C1 you have got the line integral 1 by 30. Next we go along C2. Let us now go along C2. Along curve C2 we have line integral C2, or we write along C2 what are constituents. Along curve C2, what is your C2? It is your C2. We have y square is equal to x, means I have to use dx there, 2y dy, and I have to use xy square. This will be converted when I replace dx by 2y dy and x by y square. This will be converted in y. Y will be from 1 to y is equal to 0. So what is this line integral along C2? Along C2, this is equal to integral C2, that integral. This is, I have to replace there, it is x I have to replace by y square, it is 2y square, there it is y square. Then you have dx, I have to use dx there, 2y dy, and then plus I have there 3y, y I need, it is 3y minus 4x, it is minus 4y square dy. Let me simplify this now. Well, this gives me integral y from 1 to 0, it is 4y cube dy plus integral 1 to 0, this is 2y cube dy, then plus integral 1 to 0 3y dy minus integral 1 to 0, it is 4 here, y square dy. Let us see what it is. It is 4 by 4 y4, it is 1 to 0, then plus 2 by 4 y4, it is 1 to 0. I am integrating it, simple integration, n plus 1 by n plus 1, plus 3 by 2 y square from 1 to 0, then minus 4 by 3 y cube from 1 to 0. Let me see what is. When I give the upper limit, it is 0 minus 1. This will be your 0 minus 1 plus 1 by 2. This is also 0 minus 1. this is plus 3 by 2, this is also 0 minus 1, this is minus 4 by 3, this is also 0 minus 1. And what is this now? It is minus 1 by 2, this is minus 3 by 2, it is plus 4 by 3. Okay. Let me take here simple way 6 LCM. This is your minus 6, this is minus 3, this is minus 9, this is 12. And what is this now? It is your 9 plus 2, 11, minus 17, 12. It is minus 5 by 6. This is minus 5 by 6. You will check it at your places. Now we will write the circulation. We are in a position to write the circulation of the given force along the curve C. Thus circulation of F around curve C. Curve C is given by the two parabolas, this curve, but it has the two parts. One part is this curve, another part is this. It is given by integral of C F dot dr, which you can now say C1 F dot dr plus line integral along C1, line integral along C2, it is F dot dr. Now you have found out separately. First you have gone through this C1, but you have used the curve here this, then you have come from this anti-clockwise direction this way. It is the closed path. It is the closed path. We should remember, we should always, when we want to have a closed path, every curve should lie on our left. The open part lies on our left. It is closed path. Well, when we move along the edges, it should lie on our left. Now from this on C2, we have this C2 curve, and we have actually found these separately. This was your F dot dr C1, it is 1 by 30, and this is your minus 5 by 6. What is this? We have 30 here LCM. It is 1 minus, yes, when 30, it is here, it is 525. If I am right, you can go accordingly. I have got here minus 5 by 6, there it is 1 by 30, take 30 LCM, it is 1 minus 24 by 30. You can write it is 4 by this is the circulation. You should check these numbers here. Is 1 by 30 okay, and minus 5 by 6. The procedure is same. Use this here, here, then subtract the 2. You will get the required result. This is how we find out the circulation when we have the curve which is connected by actually what? It is connected by two curves. When two curves intersect, we have to find out the circulation. Then we use two parts separately. One circulation along this part plus circulation along this part gives the whole circulation. Thank you very much. We will be doing some more applications on this line integral next. Thank you very much.